In this lecture, we're going to finish up our mathematical preliminaries by taking a look at derivatives. So let's first look at our basic definition of a derivative, and then we'll extend this to multiple dimensions and also talk about derivatives in time. So if we go all the way back to calculus, we can find the definition of a derivative that we'll write this way. df by dx is the limit as delta x approaches 0 of the function f evaluated at a position or a point of x plus delta x minus f of x divided by delta x. And that's pretty common, and we've seen that before in different classes and used it in different ways. In fact, sometimes we get so used to doing derivatives that we sometimes don't remember the basic definition. But it is always helpful to go back and kind of think about the basic definition from time to time. Let's draw a graph of a function and let's talk about this. So if I have a sketch where on my x-axis, my horizontal axis, that's my x position, and then the y values would be the functional values evaluated at all the different positions x. If my graph looked, let me use a different color. If my function was to be plotted, maybe looking something like this kind of curvy shape like this, then I could talk about a position x, and I can talk about a position x plus delta x. And I can evaluate that function at position x. And I can take this over to here. That would be the function evaluated at that particular position x. And I can do the same thing for position x plus delta x. I'm trying to draw a straight line here. And then that would be the value of f of x plus delta x. And so on the top, what we have are the difference between the function evaluated at x plus delta x and the function evaluated at x. What we have is the rise in this curve between those 2 points. So if I were to make a little triangle here, this height would be f of x plus delta x minus f of x. Of course, on the bottom, it's the distance right here is the distance delta x. And so an interpretation that I'm sure you're familiar with is that in the limit, we have a slope here between these two discrete points to be found by taking the rise over the run. But in the limit, as delta x goes to 0, it's the slope of this line at a particular point. So then again, the derivative can be thought of as the slope of a function at a point, or as the rate of change of a function over an infinitesimal distance. So in elasticity, we're going to often deal with functions that vary with spatial coordinates, x, y, and z. Some of these functions are going to be what are called scalar valued, and some are going to be what are called vector or tensor valued functions. So we'll be interested in finding derivatives of not only scalar valued functions but also vector functions. All right, and so there are some notes there on that aspect. So most of the time we'll be dealing with things that change in space in our class. There will be occasions where we'll need to look at rates of change in time. That'll be more for dynamic problems, and when we take a look at things like waves and solids, then we will look at things that change in time. So let's take a look at a scalar point function. Now, to represent a scalar, scalar function, I'm just going to have this f. There's no line underneath here or anything. And it's a scalar point function, meaning I put in a point whose coordinates are x, y, and z. I put it into that function, and out comes a scalar value. Now, physically, an example of this might be something like a density function for a fluid. If we think of a stratified fluid, maybe sitting in some container, it may have a high density material down at the bottom, indicating that with these longer lines. But as we move up the tank, the density may get a little less. The lighter things will kind of float to the top. And so in this case, if I represent the density as rho, the density could be a function of x, y, and z. And in particular, it might be a function only of z, but in general, we can say it could be a function of x, y, and z. So down here at the bottom, we would have a high density, and over here at the top, we would have a low density. Now, a lot of times in our class, we're going to want to deal with continuous functions. There will be some exceptions to that, but continuous functions will meet certain differentiability requirements, which will be nice for us to deal with in this class. So in this case, we'll just say the density changes continuously from the bottom to the top. Now we may be interested in the changing of the density or the rate of change of the density. And so we're going to introduce a term. You've probably heard of this in calculus. It may have been a long time ago. But we're going to introduce a term called the total differential of a function. So if we have a scalar point function, call it f, and if f is a function of those spatial variables, f is equal to a function of x, y, and z, something called the total differential is going to be given by the following expression. df is partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy plus the partial derivative of f with respect to z dz. Now we see some interesting terms in here. First of all, we have rates of change of that function in the x, y, and z direction. So we can say that the change in f, the df, is given by the summation, or the sum, of the rates of change in each spatial direction and the rate of change being something like the partial derivative of f with respect to x, or the other two that we have there, times the amount of change in each direction times the amount of changing position in each direction. Let's just write it this way. Times the amount of small distance in each direction. And this would be like the dx, the dy, and the dz. If we thought of this as kind of a not an infinitesimal, but kind of a large change in f, or a finite a change in f. So this would be the rate of change of the function in the x direction times that little bit of distance in the x direction, plus, go ahead and write it all out, rate of change in the y direction times the amount of distance in the y direction, plus the rate of change in the z direction times the amount of distance in the z direction. Okay, so that's the total differential. And this is, of course, provided those differentiability conditions are met. Now you can take an entire class, entire lifetime's worth of calculus classes, and you can get into a lot more details than what we're providing here. But again, this is meant to be more of a refresher from maybe an undergraduate calculus class that you might have had. So let's look at this in just a little bit more detail. There are a couple ways to examine this, but one of the approaches that we're going to take right now is that we have the set of infinitesimals, the dx, the dy, and the dz. We can actually think of that set of infinitesimals as their own vector. And so I'm going to have a vector that I'm going to call ds, okay, see with the line underneath it to indicate a vector, and it's going to be dx in the I or e hat one direction, plus dy in the j or e hat 2 direction, plus dz in the k or the e hat 3 direction. And I can do some different things with this. I can certainly find the magnitude of this. We know how to do that. We would denote the magnitude of ds this way, and I'm going to call that ds without any line underneath of it. So this is a scalar. And the way that we could find it is we could take the dot product of itself and then take square root, or we could just know that it's going to be like a dx squared plus a dy squared plus a dz squared, each of those infinitesimals to the 1/2 power. If we wanted to plot this vector on an xyz coordinate system, we could do that. Okay, so that vector is from the origin dx, dy, and dz. And since this is the magnitude, we can find a unit vector in the direction of this infinitesimal vector. That can be found by taking dx by ds dy by ds, and dz by ds. I keep wanting to try to put an x in there. And what I would always tell my students in class is keep a really close eye on me. There are a couple things that I need to be very careful about. Of course, getting those subscripts right, getting indices correct, and getting partial and straight derivatives correct. So I will really try hard when I make these videos to not make any mistakes like that, but I guarantee at some point I'm going to end up making a mistake. Well, as this unit vector, these can also be interpreted as direction cosines. We've talked about direction cosines before as well. So cosine alpha can be this term, cosine beta can be the second term, and cosine gamma can be the third term. And so we have alpha, beta, and gamma to form the direction cosines along that infinitesimal unit vector. And we can even call this u if we would like. And then the magnitude of that u would be equal to 1. Again, we can see that because if these are direction cosines, if we do that interpretation, cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. And if we take that to the 1/2 power, that is still equal to 1. Okay, so again, that term that I have here is the total differential. And we can get at something called the total derivative of the function f. By taking that, go ahead and write it down. And multiplying both sides by 1 over ds. Okay, so we can have df by ds is the partial derivative of f with respect to x, dx by ds plus the partial derivative of f with respect to y, dy by ds plus the partial derivative of f with respect to z, dz by ds. Okay, and so this is called the total derivative of that function. Okay. Slight difference in those terms. Now, what we had previously was each of these terms that I'm going to circle here were equivalent to direction cosines. We change colors. So this we had the cosine of alpha, cosine of beta, and the cosine of gamma. So we can think of that in that way as well. Let me rewrite this one more time. And there will be certain times where we'll want to think of it like the top equation with the dx by ds in it. There will be other times when we want to think of it as the bottom equation that has the direction cosines in it. Now with these direction cosines, we can use our index notation if we would like, and we can write this in this manner: partial of f with respect to x sub I cosine theta I, where theta 1 is alpha, theta 2 is beta, and theta 3 is gamma. And of course we could do it in terms of the other expression as well. The partial of f with respect to x sub I dx sub I ds. Okay. So those are equivalent expressions, and these are both ways that we can use our index notation to express the total derivative. Now this form with the direction cosines is also known as a directional derivative. Okay, so just another term you may have heard. It depends on ds, the vector. Okay, now we're in a position to talk about something called the gradient. Let me make a clean page here. Alright, so the gradient is one of these terms that I think is pretty neat. I've often heard people say that life cannot exist without water, and I would claim that the universe cannot exist without a gradient. A gradient is just a pretty neat thing. So we've talked about this term, the total derivative df by ds, and we said one way to write it was in terms of the directional derivative, partial of f with respect to x sub I cosine theta I. And this cosine theta I term, if we think of that as a vector, what we have is our two terms that are added together, and it's almost like a dot product of two vectors. This cosine theta I vector, okay, is by definition a unit vector. What we're going to do is we're going to define a term here that the first term is we're going to call the gradient of that scalar function f, and then it's going to be dotted times a unit vector n. Alright, so what is the unit vector n? Alright, so it's cosine theta 1 e hat 1 plus cosine theta 2 e hat 2 plus cosine theta 3 e hat 3, or in terms of the other symbols that we've been using before, cosine alpha, cosine beta, and cosine gamma. I need a J right here. And of course, then the magnitude of n is equal to 1. And the other term, the gradient term, then we're going to use a special symbol, del f. Okay, so grad f, same thing as del f. It's going to be defined as a vector that's made of these rates of change, partial of f with respect to x in the I direction, plus the partial with respect to y in the j direction, plus the partial of f with respect to z in the k direction, or in terms of our other notation, our 1, 2, 3 notation, partial of f with respect to x1 e hat 1 plus the partial of f with respect to x2 e hat 2 plus the partial derivative of f with respect to x3 e hat 3. Or if we want to put this together in our implied summation notation, we could say something like the partial of f with respect to x j e hat j, where we have that summation. Now when we take partial derivatives, we have kind of an interesting thing that we can do. We can pull that f out in front and have an operator operating on f. So let's take a look at this first term. We can think of this as the partial of something with respect to x1 that is operating on the function f, and its result is in the e hat 1 direction. And we can do something similar with these other terms here. See, I'm kind of writing that f out to the side. And so what I can also do then is I can take that f completely out of this entire operator. So I can have a partial with respect to x1 operating on nothing at the moment in the E1 direction, partial with respect to x2 operating on nothing at the moment in the E2 direction, and the partial with respect to x3 operating on nothing at the moment in the E hat 3 direction. And I need to include that term in here. Okay, let me make a little bit more room. Oh, and I forgot to put my operating on f out to the side here, so I need to do that as well. All right. So I made a little bit more room, and what we have is our function f out to the right side, and we have this stuff that's in here, and so that we can define as this symbol, this del. It's upside down delta. Some people call it nabla or aleph, but I'm going to call it del, operating on that function f. And so what is that? Well, that's this term right here. Okay, so that term is what we call a linear operator. It's just sitting here waiting for a function f to be plugged into here, and then we can find a vector from our scalar point function. So del is something that turns a scalar point function into a particular kind of vector based on gradients. Alright, so let's write that down. Del is going to be defined as partial with respect to xi, e hat I, and same if we were to run that sum out. This is a linear operator. We should talk about what linear operators are. And it transforms a scalar point function into a vector. Okay, linear operators must possess two qualities. If f is a linear operator, whatever f is, in this case it's specific del that we have, then first of all, if we take that operator and operate it on two scalars, a plus b, then we have the same result as if we operated on those two scalars independently and then added the result. F of a plus b is equal to f of a plus f of b. And then if we had a multiplier times whatever it's acting on, then a linear operator would be the same as if we factored out that multiplier and evaluated that operator on a, and we would end up with the same result. Now, a lot of things that you've worked with already are linear operators, but it would be useful to give a counterexample just so you don't think that everything is a linear operator. And so if we looked at something like the sine of a plus b, okay, that is not the sine of a plus the sine of b. Okay, so the sine function is not a linear operator. In fact, sine of a plus b is equal to sine A cosine B plus cosine A sine B. Okay, and you can think of other things that are linear operators or not linear operators as well. Okay, well, let's go back and take a look at our gradient. Partial of, well, not f, but the partial sitting here, waiting to operate on some function. Partial with respect to xi, e hat I. If we think of that as a vector, we can do all kinds of interesting things that we do with vectors. One of the things that we've done already is we've taken the dot product of itself, a vector with itself, and we do that in this case as well. We know how that works. We have our implied summation notation. It's the partial with respect to xi, partial with respect to xi. If we were to expand this out and use our xy z notation, well, we can write it as the second partial of this with respect to xi and xi. Notice with it, if we write it this way with our index notation, we have to leave the bottom as two separate x sub i's. We can't say that it's the second partial of something with respect to the second partial xi, because that gets rid of our implied summation. So we need to leave that implied summation in place. But if we were to expand this out, then this would be like the second partial with respect to x twice, waiting to operate on something, plus the second partial with respect to y twice, waiting to operate on something, plus the second partial with respect to z twice, waiting to operate on something. And this has a special name, and we use a special symbol for this. This is del squared. Notice that there's no line underneath of it. This is called the Laplacian operator. Now, you may have had classes where you've used the Laplacian operator. Like something like del squared f is equal to 0. Maybe you've talked about the wave equation in some other class. We will talk about the wave equation in this class a little bit later. And so this comes up pretty frequently. You may not have approached it from the dot product of the gradient with itself, but you may have just started with calling something del squared f and then using that operation directly. So in this case, this would be something like second partial of f with respect to x twice, plus the second partial of f with respect to y twice, plus the second partial of f with respect to z twice, equal to 0. So whatever equation or physical meaning that has, you can interpret it that way. There's also another interpretation of the gradient to something called level surfaces in the steepest descent. So let's make a new page and we'll talk just a little bit about that. Okay, so we can have an application to level surfaces. And again, we'll write down our gradient. And we can do this in terms of spatial coordinates and our ijk notation. And then, of course, if we had that operating on a scalar point function f, then we get the vector partial of f with respect to x, the I direction partial of f with respect to y, the j direction, and a partial of f with respect to z in the k direction. Alright, so now what I mean by a level surface would be something you might see on a topographical map. A level surface is something where the functional value has the same value everywhere along that contour. So maybe we're looking down at a topographical map and there's a certain elevation. In this certain elevation, I'm just going to make up a number. Maybe that's 1,000 feet. And then we have another elevation line. Everywhere on this line is 500 feet. And then we have another line where everywhere along that path is 250 feet. Okay, so these would be level surfaces. If we had an expression for the function, I'm kind of drawing ellipse-ish type shapes, so you can think of this as an ellipse in 2D if you would like. But if we took a look at the function evaluated at a particular point, if we evaluate the gradient at that point and look at that vector, then that gradient vector would point perpendicular to the surface in that sort of direction. So this would be del f. Now if this is a two-dimensional plot, it's only going to be a function of x and y, but that would be like of x naught and y naught. So the gradient would point in that direction. So this might be the function, let me change colors here, f1 equal to c1, f2 equal to c2, and f3 of x and y. And put that on the others, but equal to c3. And the c1, c2, and c3 would be things like the 1,000, 500, and 250 feet values. Now if we move along a level surface, by definition, df is equal to 0. Because these represent values of constant elevation or what have you. So if I'm at this point and I move over to this point, my functional value hasn't changed, so my function hasn't changed, my df is 0. Okay. So we can think of a unit tangent that goes along this path here. Maybe that's t. And the gradient represents the path of maximum change. Now, may have to scoot this up just a little bit to make a little bit more room. Since df is equal to 0, so would df by ds. And then that tangent vector dotted with the gradient would also be equal to 0. And so the tangent vector and the gradient of the function at that point are going to be perpendicular to each other. I teach a class in plasticity, and in that class in plasticity we talk about yield surfaces in materials and metals, and oftentimes we're needing to calculate the normal vector and the tangent vector on a particular yield surface. And so we can do that pretty easily by evaluating the gradient. Alright, so in general we can say that del f tells us the rate of change of the function in those three directions at a point in terms of a vector function. Well, with this information then, I think we're about ready to put everything together with our math and start talking about some actual continuum mechanics, which will be the background information again that we need to get into the specialization to theory of elasticity. Now, in the class that I teach and we'll be teaching here, we're going to do our continuum mechanics first and then do the specialization. The nice thing about doing the continuum mechanics first is that it applies to other fields besides elasticity. It will also apply to plasticity and fracture mechanics and fluid mechanics and flexible body dynamics and so forth. So that's a good background. If you have a class in continuum mechanics, you go into more depth than I'll be able to go into as we teach elasticity. So I would encourage you to either take a class in continuum mechanics first or second after you've taken a class in elasticity. Alright, well, I think that wraps it up for this mathematical preliminaries, and as I said, then we'll get into our theory of deformation in the next section.